Okay, let's talk about deductive reasoning this time. So, inductive reasoning involves looking at patterns and making predictions that are called conjectures. And deductive reasoning which is also called logical reasoning, is the process of using true statements to arrive at a conclusion, and this conclusion is known as a theorem. It's important to understand that when we talk about a theorem in science, or where you use a lot of deductive reasoning, it's not the same as a theory when I've got a theory about how something happens. Okay, I want to put that out there. Okay, example, write a conclusion that can be deduced from each pair of statements. So every whole number is an integer, and 6 is a whole number. Therefore, I know that 6 is an integer. And I could do this with Venn diagrams, actually. If I start off with, here's my bag of integers, and my whole numbers are inside here. And because every whole number fits in that envelope of integers, and 6 is a whole number, well, 6 is also inside the bag of integers. Okay. This one says all students are teenagers. So if I have my box of teenagers and my bag of students is in here, because all students are teenagers, and Lucy's a student, then Lucy is a teenager. Yes, I know what you're going to say, and I'm going to say it. There's a flaw in this argument in that not all students are teenagers.
My brother would be a teenager under that, and he's 10.
I'm a student as well because I'm going to school myself. But if we're talking about and I can, when we are quizzing this or working on this, if I tell you that this is true and that this is true, and then I want you to draw a conclusion, then you just take it as given that these things are true, okay? Except in the section where we're talking about logic flaws, okay? And then I'll ask you to point out that not all students are teenagers. So this is a fallacious argument because it's not, your initial assumption is not true. Okay, example 2. To promote sales between noon and 2 p.m., a local pizza shop says your pizza will be free if it's not ready in 5 minutes. When Tabitha was there, the following statements were true. It was 1:30, and it took 7 minutes for her pizza to be ready. What can Tabitha deduce?
She gets free pizza?
Yeah, I wouldn't go quite that far. I would say her pizza should be free. But that's because of the way the market works. But yes, her pizza should be free, right? That's the assumption she should be able to make. Okay? And I'm going to give you just 5 minutes to do. Oh no, wait, you've got. I don't have the whole package here. So there is. Oh, there's actually quite a bit. So yeah, go ahead and work on this for a bit, and then we'll see if we have time for me to do the second part of this today. Okay? All right, using symbolic language. Deductive reasoning often involves the use of symbolic language, meaning we use symbols to represent things. To represent, for example, any number or any integer or any angle. And I did an example in class on Thursday where I said like 2n plus 1 equals 5. We use deductive reasoning to figure out that n has to equal 2 because we start with this true statement, subtract 1 from each sentence, each side, and I get a new true statement of 2n equals 4. Divide both sides by 2, and I end up with another statement of n equals 2. So I've used deductive reasoning to say that n has to equal 2 in that initial equation. It's the only answer that works. Okay. Before we go any further, there's just some more vocab for you and some conventions. So one convention involves labeling triangles. And the convention is uppercase letters are used to label points, including vertices. And the singular is vertex. So I can label this as A, B, and C. And those letters are referring to the points. Okay. Lowercase letters are used to represent side lengths. And I didn't write this down here, but in a triangle, you always give the side the letter that corresponds to the opposite vertex. So this is C and this is B. Okay. So we use the uppercase for the angle or for the vertex, and the lowercase letter for the side length. And then we use Greek letters to represent the size or the measure of the angle, not the name of the angle. So for example, I could use the Greek letter theta right here to represent the size of that angle. Commonly used Greek letters. I'm just going to write them out next to them so you see what they look like when I write them as opposed to what they look like when I do them on the computer. So theta is a circle with a horizontal line. Alpha is like a fish. Beta is a capital B with a tail. And gamma is a fish swimming down. Okay. And then the other thing that we'll come up against in this unit is different kinds of numbers. And you've seen all of these words before, but you might not have seen these symbols. This might be new. So this font is called double struck letters because it's like you did it once in your printing press and then you did it again, shifted just a little bit, and it's in math, different fonts have different meanings. These are the letters that we use to symbolize these things. And usually, like you write it like that. R for real numbers is usually written like that or like this with another line inside. Okay. Pardon me?
If if every font has a different meaning, then
Oh no, Comic Sans isn't. No, there's different fonts for different meanings, but not Comic Sans isn't one
Comic
of them.
Sans
Okay.
doesn't exist.
So natural numbers are the counting numbers. So like 1, 2, 3, and up. So counting numbers. Whole numbers add the 0. So 0, 1, 2, 3, and up. Um, one of my profs talked about the natural numbers are natural because um, you're they're natural. We use them all the time, right? You use them when you're very young. 1 block, 2 blocks, 3 blocks. And then the whole numbers, when you add 0, and now you're a whole person because you can understand the concept of 0. Um, I remember it because the word whole has an O in the middle of it. So that's how I remember which one's which. The integers is okay, so just to be clear on this too, the whole numbers includes all of the natural numbers, right? Every natural number is also a whole number, okay? Every natural number and every whole number is also an integer, but now with the integers, we're adding the negative versions of all of these. So negative 3, negative 2, negative 1, 0, 1, 2, 3, all the way up and all the way down. The rational numbers can be written, uh, the official definition is they can be written as a fraction of integers. So that includes all of the numbers above plus like 1/2 or negative 5 over 2 or 0.77 or 0.3 repeating because that equals 1 over 3. So we can write that as a fraction. Okay? So this can be written as fraction. As a fraction of integers. And then it's like a over b, but b is not equal to 0 because you're not allowed to divide by 0. So there's your official definition of a rational number. An irrational number is one that you can't write as a fraction of integers. And if you write it as a decimal, it never ends and never repeats. Okay? So never ends, decimal. Never ends, never repeats. So, for example, pi is an irrational number.
2 squared.
No, but the square root of 2. Because 2 squared is 4, so that's actually a whole number. But the square root of 2, okay? Or 1.01001001 dot 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 to show my pattern is continuing, but the number itself, there's a pattern that repeats there, but the number itself doesn't repeat. So that's irrational. Okay? And the real numbers are all of the above. All right? So the rational numbers, all of these are rational. Okay? And then, what color is this? No, I want the blue. Okay. And then the irrational numbers don't mix. So the irrational numbers are their own category over here. All of the other ones are part of the rational numbers. And if you take the rational numbers plus the irrational numbers together, that's all of that combined is the real numbers. Okay? Yep.
What does it say for the natural numbers?
Counting numbers. Counting.
Counting.
Yep. Okay. There is another class of numbers called the imaginary numbers, just so you know.
Oh,
Okay? There is, or they're called complex numbers, but we won't talk about them. But just so you know, like real numbers is actually a subcategory of numbers. Like there's something other than real numbers.
I don't like the fact that we just don't have that there are just some numbers that don't exist.
Okay, I'm not going to have a philosophical discussion about that right now. Okay. When we're talking about statements or considering statements involving odd or even numbers, because we will talk about that, we use this notation. An even number can be any even number can be written as 2n, where n and this e means is an element of the natural numbers. So any even number you can give me, I can rewrite it as 2 times some natural number. Okay, and anything that I can write as 2 times a natural number will be even. Right? 2 times 5 is even, 2 times 12 is even, 2 times 516 is even. Okay? An odd number is 2n minus 1. So 5, for example, would be 2 times 3 minus 1. Okay? So we'll use this on the next page. So let's just, but I wanted all of these things to be on one page for you to refer to. Okay, let's go to the next page. All right. In lesson 2.1, we used inductive reasoning to conjecture that when two angles intersect, the opposite angles, there should be two lines intersect. Two lines intersect. The opposite angles are equal. And although it's impossible to test every pair of lines, we can use deductive reasoning to prove that this is true. So this diagram represents any two intersecting lines. The O here is this point. Okay, that's like a letter O referring to that point. And when we name angles, we can do it with 3 letters if one letter is ambiguous. Like if I say angle O, you don't know which angle I'm talking about because O just refers to that point. If I say angles AOC, I'm talking about the angle that starts at A, goes to O, and goes to C, so I'm talking about this angle here. Okay, have you guys seen that before, I hope? Maybe you've seen it and don't remember it? Okay. All right. Since angle AOB, so that's AOB is a straight angle, I know that this angle, which is alpha, plus this angle beta equals 180 degrees because straight lines add up to 180 degrees. That's something that I already know. Since COD is a straight angle, I know that beta plus gamma equals 180 degrees. Therefore, my angle here has to equal my beta plus gamma. So alpha plus beta has to equal beta plus gamma. And then if I subtract beta from both sides, I'm left with alpha equals gamma. So I've proven using a series of true statements that angle AOC equals angle BOD. Okay, did you follow that? Okay, and I could use the same thing to prove that the other two angles are equal as well. Okay. All right. Also in lesson 2.1, we had a conjecture that the sum of three consecutive integers is 3 times the middle integer. Use deductive reasoning to prove that conjecture. Okay, so how can I represent 3 consecutive integers? So I'm going to say let. You guys did let statements last year, hopefully, to define your variables. Okay, it's a thing we do in math. It says I'm going to just tell you that this is how it is. So let n, if n is my first integer, what's my next integer? My next consecutive integer. If my first integer is 6, what's my next integer? Comes after 6, 7. And what did you do to get that? So you did n plus 1, right? So what's my next integer going to be? Oops, not m.
It'll be n plus 2.
It would be n plus 2, yeah. Oops, wrong color. Oh, no, 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 no. No, 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 no. All right. So let n plus 1, n plus 2 be 3 consecutive integers. Okay, so if I add them up, I have n plus 1 plus n plus 2. And if I add those up, I get 3n plus 3, right? And then I can write that as 3 times n plus 1, right? Because 3 times n plus 1 gets me 3n plus 3, which equals 3 times the middle integer. Oops. Integer. Because my middle integer was n plus 1. Okay, any questions? Okay, all right. Consider the statement, when two odd numbers are added, their sums are always even. So use inductive reasoning to suggest the statement is true. So anytime I ask you to use inductive reasoning to show me something, I want at least 3 examples. One example is not enough to show me that something is true. That's just one example. That doesn't mean anything. You need at least 3 to show me a pattern, okay? And obviously, it can be any 3 that you pick. I don't expect you to pick the 3 that I have in mind, right? So 3 plus 5 equals 8. This is just the examples that I have. 11 plus 19 equals 30. And 401 plus 3 equals 404. So there are 3 examples suggesting that yes, if you add 2 odd numbers, your sum is always even. To use deductive reasoning, I have to use variables. So I'm going to say now remember on the last page I said that to represent an odd number, you go 2n plus 1 or minus 1, doesn't matter. Let 2n plus 1 equal an odd number. But I need another odd number as well. And I can't say 2n plus 3 because 2n plus 3 is in fact an odd number, but it's a specific odd number, which is like the next odd number, and I don't want that. So I'm going to use 2m plus 1 is another odd number. And then I should say that n and m are both part of the real numbers, or that they're all both natural numbers. Okay. So I'm not like m and n are not decimals and they're not fractions, they're whole numbers. Okay. So any whole number that you give me, if I multiply it by 2 and add 1, I end up with an odd number. Any whole number you give me a different odd number or whole number you give me that I multiply by 2 and add 1 gives me a different odd number. Okay. So then I'm going to add these two together. So I'm going to go 2n plus 1 plus 2m plus 1. And I'm just going to pause for a second to say, are those brackets necessary? Are they strictly necessary or are they just helpful?
I think they're strictly necessary.
Well, I think they're not strictly necessary because if I didn't write them, it would equal the same thing. right? It's not like I'm changing the order of operations by putting them in there, but I think they're really helpful because it says I'm taking this number, oh, look, it's an odd number, and I'm adding it to this number, oh, look, it's a different odd number. So I'm grouping it in a way that helps it make more sense, and it doesn't change the order of operations. So I'm not going to mark it wrong if you don't put them in there, but I really recommend you do because I think it makes everything make more sense. All right, so if I add these, I get 2n plus 2m plus 2, which I can then factor, and that becomes 2 times n plus m plus 1. Those brackets are essential because now I know that this number is a multiple of 2. Right? Because it's 2 times whatever n was plus whatever m was plus 1, which is going to be, therefore, an even number. All right, I think we have one more example. Okay, this question, what questions very much like this are going to be on your quizzes, on your tests. You're going to be expected to do this question. Okay. Deductive reasoning can be used to demystify some party tricks that we have. So make a conjecture using inductive reasoning. So choose a number less than 10. I'm going to choose 8. If I add 7, I get 15. If I multiply by 2, I get 30. If I subtract the original number, 30 minus 8 is 22. And then I subtract 2 and I get 20. And I subtract the original number, 20 minus 8 is 12. I'd like you to try that with 5 as your initial number. See what you get. And then pick your own number for the third column and see what you get. Okay, does anybody have a conjecture for me? Yep, the result will always be 12. Okay, so that's my conjecture. Do I know that for sure? No, not at this point. But I can prove it using deductive reasoning. So what I do for deductive reasoning is I choose a number less than 10. My number is n. If I add 7, I now have n plus 7. If I multiply that by 2, I have 2 bracket n plus 7, which equals 2n plus 14. Now I've got 2n plus 14, and I'm subtracting an n, which means I now have n plus 14. If I have n plus 14 and I subtract 2, I have n plus 12. And if I have n plus 12 and I subtract n, I just have 12. You don't have to show the parts in yellow. Okay, because that was just me having um, showing my work. That was just instead of trying to do it in my head and do the subtractions and the multiplications in my head. Um, Sometimes it's helpful to actually write down what you're doing and then you do it, right? But you have to show the rest of it because you have to show those steps. And I can see now that no matter what number I start with, I end up with 12. It doesn't matter what n is, I end up with 12. So I've proven it using deductive reasoning. Does the original number have to be less than 10? And the answer is no. There were no restrictions on n. Okay? Sometimes you end up taking a square root of something and then your number has to be positive for that to work. Okay? Sometimes there's other restrictions that there might be. Okay? Okay, so that's the lesson on that's the last example, right? Okay. So I don't want you to do any of the practice work on this tonight unless you're really gung-ho on it. There's a test tomorrow. You might want to, redo one of the quizzes or something for that. But do try and get the practice work prior to this section done, okay, if you can. And then tomorrow we'll write the test, and then we'll have time to work on this, and I'll be helping you with this tomorrow, okay? But we do have 20 minutes left of class, so let's make good use of that time.